Let's take a break. After talking about domain adaptation, the video recorded by the TAs will be played in the next class. The video about domain adaptation recorded by the TAs is very clear, so we will go through it fast here. If you can't hear well, you still have a chance to listen again to the video recorded by the TAs. If you already understand the content that I would talk about later, although I speak a little fast, then when we play the video recorded by the TAs, you just take a break and do other things. Okay. Let's talk about domain adaptation. So far, we have trained a lot of machine learning models. So, for everyone, training a classifier is not a problem at all. Suppose you want to train a classifier for digit recognition. You just need to get the training data, train a model, and apply it to the testing data. It's over. The digit recognition problem is simple. You can do whatever you want and achieve 99.5% accuracy on the MNIST benchmark corpus. But if the distribution of testing data is different from the one of training data, how to do it? Let's take a simple example. When training, your numbers are black and white. But when testing, your numbers are colorful. What will it happen? You might think, although one side is black and white, and the other side is colorful. But since the shapes of the numbers are the same, if the model can recognize numbers in black and white pictures, would it be possible to recognize the numbers in the colorful pictures? Actually, it is not. If your model is trained on such black and white numbers, when it is directly used for the colorful numbers, the correct rate you get will be very low. It will be about 57%, which is not a passing score. So we know that once there are some differences in the training data and testing data, or the distribution between them is different, the model you trained on the training data may be broken on the testing data. This kind of problem is called domain shift. That is, when the distribution of your training data is different from the distribution of your testing data. This situation is called domain shift. In most of this kind of homework, or benchmark corpus, we all ignore the problem of domain shift. Our training data and testing data tend to have the same distribution. This will give everyone a wrong impression, such as, "Wow, what kind of artificial intelligence is this? It is really amazing." Or, "It is beyond human beings on many tasks." But in real applications, when your training data and testing data does not have exactly the same distribution, whether the machine can perform well is unknown. So, today we are going to talk about that. Assuming there is a little difference in training data and testing data, is there any way we can get a better result? Okay, today I'm going to talk about the technology of domain adaptation. The technology of domain adaptation can also be regarded as a type of transfer learning. How to say that? Transfer learning is that the skills you learned on task A can be used on task B. For domain adaptation, your training data is in a domain, whereas your test data is in another domain. On the training data, for the information learned from a certain domain, you need to use it in another domain, and use it on the test data. So you are applying the knowledge learned from a domain to another domain, so it can be seen as a part of the transfer learning process. In the video of the past lessons, we have a comprehensive introduction about transfer learning. But since time is limited today, we will only focus on the domain adaptation part. If you are interested, you can take a look at the video of the past lessons. Okay, domain shift has many different types. What we just saw is that the distribution of the input data changes. However, it is just one case of domain shift. In fact, there is another case. The distribution of output may also changes. For example, in your training data, maybe every number has equal chance of appearing. But on the test data, the probability of each output may be different. It is possible that a certain number has a particularly high probability of output. Is this possible? It is actually possible. Then this is also a kind of domain shift. There is also a much rarer, but not completely impossible case. Although the distribution of input and output may be the same, the relationship between them has changed. Maybe in your training materials. This kind of thing is called 0. But in your test data, this kind of thing is called 1. It's not impossible. It's also possible that the relationship between the input and the output is not identically the same in the training data and in the test data. Then this is another kind of domain shift. Today we will only focus on the domain shift with different data. Okay, in the following class, we will call the test data the training data of the target domain. Similarly, our training data comes from the source domain. The data in the target domain is our test data. Okay, so in domain adaptation, our situation is like this. We have a bunch of training materials. Here we will directly use the classification of handwritten numbers. As our example, we have a bunch of training materials. This information comes from source domain. And these training data are labeled. We know what number corresponds to each picture. But now we want to use these data to train a model, so that this model can be used on different domains. Then in order to use this model in a different domain, during training, we have to have some understanding on the another domain, which is the target domain where the test data is located. Then depending on our understanding on the target domain, we have different kinds of methods of domain adaptation. The case we have the most understanding is that we not only have data on the target domain, but we also have the corresponding labels to the data. This is one case. But there is another better situation. Maybe you already have a lot of data on the target domain. Those data also have labels. Then you don't actually need to do domain adaptation. You just use the information from target domain to train. So if you have a really good understanding on the target domain, which means there is already a lot of data, and the data are also labeled, then you don't need to do domain adaptation at all. The situation for making domain adaptation may be that you have the labeled target domain data, but the amount is very small. What should I do in this situation? This situation is still easy to handle in the domain adaptation. If what you encounter today is the case of a small amount of labeled data, you can use these labeled data to fine-tune the model you trained on the source domain. The so-called fine-tuning here was like your behavior when you were doing BERT. You already have a pre-trained model on the source domain. Then you take the data of the target domain to train with a few epochs. Okay, in this situation, the problem you need to pay attention to is this. Because the amount of data in your target domain is very small, you have to be careful not to overfit. In other words, don't use the data on the target domain to run too much iteration. If you run too much iteration, it may overfit these small amounts of data on the target domain. Then, you can't do well on your real testing set. It is possible. In order to avoid overfitting, there were many solutions in the past, like a lower learning rate. For example, you want to make the difference between the parameters before fine-tuning and after fine-tuning small. Or you can force the relationship between its input and output in the model before fine-tuning and after fine-tuning to be close. There are many different ways. We won't go into details here. Okay, the situation I mainly want to share with you today is that we have a lot of data on the target domain, which is also the situation in our homework. But these data are not labeled. Your target domain is numbers with colors. You also collect a lot of pictures with colored numbers, but no one labels what the number is in each picture. What we have to deal with in the homework is to find a solution to this. When we encounter this common situation, how should we solve it? A situation like this is a possible situation in a real system. For example, you train a model in the laboratory. You want to use it in the real field. You just put your model online. Some people actually use it. But you find that the feedback you get is very poor. Everyone dislikes that your system has a low accuracy rate. What should you do? At this time, you may be able to use the domain adaptation technology. Because your system is already online, And some people have already used it. You can collect a lot of data. It's just that the data are not labeled. The question to be asked now is, how to use these unlabeled data to help us train a model on the source domain that can be used on the target domain? The most basic idea here is like this. The basic concept here is like this. We want to find a feature extractor. This feature extractor is actually a network. This network will take a picture as input. It generates a vector, which is a feature. Although the images on the source domain and the target domain look different, the feature extractor will take away their different parts and extract only the parts they have in common. So, although for the two pictures, one has color and the other has no color, it's already very different. But we expect that this feature extractor can learn to ignore the color. It can filter out the information of color. So whether it's the picture from the source domain or the picture from the target domain, the feature it gets looks no differenced. After going through this feature extractor, they seem to have the same distribution. So you can use these features to train a model with the source domain and directly apply it to the target domain. The next question is, how to find such a feature extractor? How can we find such a feature extractor? In fact, we can split a general classifier into a feature extractor and a label predictor. An image classifier takes an image as input and outputs the result of classification. Let's say that the image classifier has 10 layers. Then we can split the layers into two parts. The first 5 layers belong to the feature extractor, while the last 5 layers belong to the label predictor. Why? The output given an image after the first 5 layers is a vector. If the model is a CNN, its output is actually a feature map. But the feature map can also be regarded as a vector. The classification result is the output of the later 5 layers of the feature vector. So we can think of the first 5 layers as the feature extractor. You might ask, why should we pick 5 layers? Why not pick the first 4, or any other number? Well, this is up to you. You can freely decide which part of the classifier belongs to the feature extractor or the label predictor. Actually, the number of layers picked can be regarded as a hyperparameter, which need to be adjusted. Later on, we are going to use a method called domain adversarial training. When using domain adversarial training, you also need to decide which part of the classifier is used as the feature extractor by yourself. So how can we train the feature extractor and the label predictor? The data in the source domain are labeled. Just throw it into the classifier and force it to produce the correct answer after passing through the feature extractor and the label predictor. But there is one slight difference. We have a bunch of target domain data, but they are unlabeled. These data are not marked, so we cannot use the output of the label predictor to train it, because we don't have the correct answer. How can these data be used? The answer is, we throw these images into the image classifier and take out the output of the feature extractor. We hope that the feature extractor's output for both source and target domain images to be indistinguishable. The blue dots represent the feature of images from source domain. The red dots represent the images from target domain. We want to minimize the difference between the blue and the red dots. How to make the blue dots and the red dots indistinguishable? It has to rely on the technology of domain adversarial training. It is totally fine if you didn't totally understand this part. The tush will go over the details again later. Okay, what we have to do now is to train a domain classifier. The domain classifier is a binary classifier. The input is this vector, and it needs to discriminate whether the vector is from the source domain or the target domain. It has to discriminate whether this factor is from the source domain or the target domain. The learning goal of the feature extractor is to think of a way to fool the domain classifier. The process of fooling might remind you of GAN. In other words, the generative adversarial network. That's right, the domain adversarial training is pretty much like GAN. You can think of the feature extractor as a generator, and think of the domain classifier as a discriminator. The first paper of domain adversarial training, if I remember correctly, is published on ICML in 2015. Just a little bit later than that GAN. But they can be viewed as works almost at the same time. In the paper of domain adversarial training had a reference to the paper of GAN, but at that time, the paper of GAN had not been accepted by NeurIPS. The only thing it said is that there is another paper proposed a method called GAN, posted on the internet, have some similarity with this work, so they can be regarded as contemporaneous works. However, the domain adversarial training still has a little difference compared to the GAN. It seems that the generator has too much advantage over the discriminator. For the generator, there is a really naive way to fool the discriminator, which is the feature extractor, or the generator. Output 0. No matter what the input is, the output is always the zero factor regardless of the input. Then the domain classifier will have no clue of what the input image looks like. The zero factor is what it can see. So there is no way it can distinguish which domain the factor comes from. But this is obviously not what we want to see. If the feature extractor will only output zero vectors, then it is totally useless. Will this situation happen? Actually, it won't happen. Why? Because the label predictor also needs this feature. The label predictor also needs this feature to judge which category does the input image belongs to. If the generator outputs zero vectors, no matter of the input image, for the label predictor, it has no way to determine which picture it is. In this case, because the feature extractor still needs to generate the factor to make the label predictor produce the correct answer, the feature extractor cannot always output zero vectors, regardless of the input. Now, we will go over the above process again with symbols, just to make it clear. Assuming the parameters of label predictor is theta p, the parameter of domain classifier is theta d, and the parameter of feature extractor is theta f. Then these images on the source domain has a classification cross-entropy, because the images in the source domain have labels, so you can calculate their cross-entropy. Based on their cross-entropy, we can design a loss for theta p. Oh, I haven't talked about theta p yet. There is an L here. L is the cross-entropy of those images on the source domain, which is calculated according to their labels. Then for this domain classifier, it has to find a way to distinguish the gap between source and target domain. It is actually doing a binary classification. This classification problem has a loss called LD. Then we are going to find a theta p to make this L as small as possible. We are going to find a theta d to make this LD as small as possible. What the label predictor does is to make the classification of the images in the source domain as correct as possible. The domain classifier aims to make the classification of the domain as correct as possible. As for feature extractor, what feature extractor does is to stand on the side of the label predictor and fight against the domain classifier. That is, it does the opposite things of domain classifier. So the loss of feature extractor is the loss of label predictor, L, subtracted by the loss of the domain classifier, called LD. So the loss of feature extractor is the L minus LD. You have to find a set of parameters theta f, making the value of L minus LD as small as possible. This is the most original method of domain adversarial training. But is it the best in practice? You can think about it. We won't go into details. Everyone can think about it and discover for themselves. Think about it. Assuming the job that the domain classifier does is to separate the source domain from the target domain. For example, it wants to know that its feature comes from source domain. Upon seeing this kind of picture, or it wants to know that its feature comes from target domain. Upon seeing this kind of picture, it needs to separate these two groups of features. If the loss of the feature extractor is a minus sign added on the domain classifier directly. What does that mean? It means that the feature extractor's job is the opposite of domain classifier. Originally, domain classifier classifies the feature of this picture as source. Now, feature extractor aim to let domain classifier classify this picture as target. For this picture, in turn, as source. If you do so, didn't you also separate the two groups of features? What we are going to do now is to eliminate the difference between the source and the target domain. But either you use LD or still negative LD. It's all necessary to separate source domain from target domain. Originally, domain classifier is to make the value of LD as small as possible. It is now negative LD. Feature extractor should make the value of LD the bigger the better. In fact, it also separates source domain from target domain. So this may not be the best practice. Of course, this trick works. But how can we do better? We leave this question for everyone to discover the answer yourself. That'll be some food for thought for you guys. Now, let's take a look at the original paper on domain adversarial training. What is the result of it? When I saw this paper back then, I was really amazed by the results. It did 4 tasks, all of them being basically digit recognition. The upper part is the image from the source domain, and the bottom half is the image from the target domain. Now, if we were to use the images from the target domain for both training and testing, the result would look something like this. The accuracy of each task is above 90%. However, if we were to use the images from the source domain for training and the images from the target domain for testing, we would be training on black and white digits and testing on colored digits. The result would be quite poor in comparison. The accuracy of it dropped significantly. Now, if we add domain adversarial training, what would the result look like? Originally, when it was trained on black and white images and tested on colored images, the accuracy was 57.5%. When we add domain adversarial training, the accuracy soared to 81%. The improvements in many other tasks are also quite substantial. From 59% to 71%. From 74% to 88.7%. The improvement is quite evident and significant. That's domain adversarial training. Okay, let's pause for a bit and see if there's any question. Okay. Let me see. Someone asked if the domain classifier is similar to something like the k-means clustering. Well, no. It is a binary classifier. The domain classifier is simply a network that can have many layers, and you can decide how many layers it has. So, it is not a k-means clustering. It is just a classifier. We train the classifier. That takes the feature vector as the input and outputs whether the input belongs to the source domain or the target domain. Wait, someone has already answered that for me. It seems that the teaching assistant has already answered that question for me. Fine, let's continue. Okay, there are still some limitations to this idea. There is a small problem. What is it? Let's take a look. The blue circles and blue triangles represent 2 classes on the source domain. Of course, we can find a boundary that separates these 2 groups of classes. For the data on the target domain, we don't have its class labels. We can only say that all the data from the target domain are represented by squares. The goal of the training is to make the distribution of these squares align to the distribution of the circles and triangles as much as possible. What does it mean to align them as much as possible? In the case on the left, the red dots and the blue dots are pretty aligned together. Their distributions are somewhat close. In the case on the right, The red dots and the blue dots are also pretty aligned together. Now, which one do you think is better? Is it the one on the left or the one on the right? Let's try to have some interactions. If you think left is better, enter 1 in the chat. If you think right is better, enter 2 in the chat. Let's see if there is a way to interact with you guys. I can answer the classmates' questions when waiting for your choices. What does the percentage in parentheses after the proposed approach mean? That percentage is the amount of improvement. It is the amount of improvement. It does not have special meaning. Okay. A student asked. The training data only has source data. Oh, he is answering other students' questions. It is good. Okay, most students choose 2. Most students choose 2. Some students also choose -1. It is good. There are so many 2 in the chat. I think most of the students think right is better. Yes, many people choose right. Should we let the situation on the right happen and avoid the situation on the left? How to do it? How to make the situation on the right happen and avoid the situation on the left? We have a simple idea. We know where the decision boundary between the blue circle and the blue triangle is. We know this decision boundary. We should make these squares. Although we don't know which category it is, we should keep these squares away from this decision boundary. How to keep the square away from this decision boundary? There are many different methods in the literature. You can refer to the literature. See what kind of method is better. For example, one of the easiest ways is this. We have a lot of unlabeled pictures. Feed pictures to feature extractor. And then feed to the label predictor. Although I don't know which category it is. I hope it is as far away from boundary as possible. What does it mean to be far away from boundary? If we have a very high score in one category, is called far away from boundary. If output probability of categories is close, is called near the boundary. Feed the unlabeled image into feature extractor and then feed it into the label predictor. Make output result as far away from boundary as possible. In other words, to have a high score on a certain category. Although we don't know which category it should be. At least it should be in one category. This is one but not the only trick. Then you can refer to the literature. For example, there is a well-known method called dirt T. Dirt T. In the paper, the authors told you dirt T should pronounce dirty. You have to pronounce it dirty. Everyone is a master of naming models. Everyone will name some very creative names. Well, this dirty is a trick. There is another trick called maximum classifier discrepancy. If you want to get the best results in this domain adaptation homework, these tricks are indispensable. How these tricks work is complicated. I'll leave this to everyone's own research. There is another problem here. What kind of problem is it? So far, we assume that the source domain and the target domain have exactly the same categories. Source domain is a problem of image classification. Source domain has categories of tigers, lions, and dogs. Target domain should also have categories of tigers, lions, and dogs. Will it really be like this? Target domain does not have a label. We don't even know what's inside the target domain. We don't know what category is inside the target domain. And in this illustration, the solid circle represents things in the source domain. The dashed circle represents things in the target domain. So is it possible that there are more things in the source domain than there are in the target domain? Is it possible that there are fewer things in the source domain and more things in the target domain? Is it possible that the two overlaps, but each also has its own unique category? It's all possible. So under this premise, aligning source domain and target domain sounds like a problem. Because for example, in this case, you said you want the data's feature in the source domain and the data's feature in the target domain to completely match together. That means you force the tiger to be like a dog, or force the tiger to be like a lion. Eventually, you won't be able to distinguish the tiger category. Sounds like a problematic method. So how to solve this problem? What to do when source domain and target domain have different labels? You can refer to this article. Universal domain adaptation. Let's see if anyone has questions to ask. Okay, one asked. If feature extractor is CNN instead of a linear layer, then the input of the domain classifier is a latent embedding that is straightened from the feature map. Will domain adaptation affect what the latent space has learned? Because feature map originally considers space, and now it's just being straightened? You are right. Really, that's totally true. Feature extractor is a complex network. If we want to pull the things of the two domains together, they may only come together for the sake of coming together and do not learn anything. We expect this feature space to learn. The simple answer is yes. Yes. So domain adaptation is not as easy to train as you might imagine. Although it seems that everything went smoothly just now, you can experience it yourself in the homework. Domain adaptation is a rather difficult homework. So, when we are training, we have two things fighting against each other. One is to cheat the domain classifier. The other is to make the classification correct. We expect these two things to be done at the same time. In other words, on the one hand, it has to fool the domain classifier. On the other hand, it has to classify well. So we align the two domains together at the same time. At the same time, we hope latent space's distribution is correct. For example, we think 1 is more like 7, because we want to make the classifier do a good job. Your feature extractor will make 1 and 7 look more alike. Then, for example, 1 does not look like 4. It will move 1 and 4 a little further. We expect that, through optimizing to increase the performance of the label predictor, the space in the latent representation still keep a better latent space. But it may not always be successful. If the weight for fooling the domain classifier is too great, your model will learn that to just fool the domain classifier, and it won't generate a good latent space. So, the issue mentioned by the classmate might happen. So, when everyone is practicing in the homework, there are also some parameters to adjust. Alright. I hope I have answered the question. Okay. Next, there is a more severe situation. Previously, we assumed that there is no labeled data. But, there is a lot of data at least. At this time, you can even say that I want to pull two spaces together. However, there are one more possible situation. In addition to having no labels, we also don't have much data. For example, I only have one image. You only have one at this time. Your target domain only has one image. It only has one point in the latent space. You have no way to align it to the points in the source domain. What should we do now? Assuming that there is little data in the target domain, what should we do? It's not impossible to do. There is a method called testing time training, which is abbreviated as TTT. We attach the link here for your reference. Testing time training is to deal with the following situation. Assuming there is no label in my target domain, and there is only one image. Testing time training provides a solution in this situation. But, there is actually a more severe situation. This situation is, if we don't know anything. If we don't know anything about the target domain, what should we do? At this time, it is divided into two situations. For the problem that we have no knowledge about the target domain at all, we will not call it domain adaptation. Usually, we call it domain generalization. Because we are not going to adapt to a specific domain. We don't know anything about that specific domain. We are looking forward to making the machine learn. Domain generalization. During testing, no matter what magical domain comes, it can always handle. For domain generalization, it could also be divided into two situations. One situation is that the training data are very rich, originally containing a variety of different domains. We assume that you want to make a classifier to separate cats and dogs. Now, in the training data, there are real pictures of cats and dogs, and sketches of cats and dogs, and watercolor pictures of cats and dogs. We expect that the model could learn to diminish the differences between domains, because there are different domains in the training data. Now, if there is the cartoon pictures of cats and dogs in the test data, it can also handle. This is one situation, which you can better imagine how to deal with it. So, we won't go into details here. We only put some representative papers for your reference. But, there is another situation, which you will feel that you really don't know how to do is the situation where there is only one domain in the training data. If there is only one domain in the training data, and there are different domains in the test data, how should you deal with it? It's not no one tried in the literatures. There are some people trying to solve this kind of issue. What do? We won't talk about the details. Conceptually, it's a bit like data augmentation. Although you have data in only one domain, you could come up with a data augmentation method to generate data for different domains. Then, you can do it with the scenario above to see if it can work in the test data of the new domain. Okay, this is domain generalization. Okay, we just talked briefly to everyone about the different techniques of domain adaptation. For more details, in the next class, the TAs will explain to everyone carefully. We now are going to take a 5 minutes break. You could take a break and come back later.